All right, so exam 1 is Friday. What would that be, the 3rd? I think that's right. And the topics are everything up through strain and constitutive relationship. So Wednesday we'll probably get into some material that's not going to be on the test. We'll get into principal stresses, but the stuff we're going to talk about today is going to be on there. And the only thing that we have left in strain and constitutive relationships that we haven't talked about yet is rotating coordinate systems, re-expressing stress tensors in a new coordinate system. We started to talk about the rotation matrix. But, yes, so compliance and stiffness matrix will be on there. Stress will be on there. That simple assignment, or I don't know about simple, but that short assignment on matrix math, you need to know all that stuff. And then vectors. All right, so last time we started talking about rotation matrices. And the way that I said it, the sort of general definition, this isn't the one we're going to use in this class, but this is, you can think this is always true. To re-express a vector in coordinate system A in coordinate system B, the columns of the rotation matrix are the coordinate axes of A expressed in coordinate system B. So I don't know, that helps me remember it because you're talking about going from A to B, so the columns are A expressed in B. That's not how we're going to do it. We're gonna use rotation matrices about the individual axes. So here's going to be our approach. And this approach, by the way, is sometimes useful, but we're just not going to do it that way. So our approach says to rotate a coordinate system, an angle theta about, and so I'm going to go one by one through the axes. And you need to keep in mind, okay, so is this thing rotating clockwise or counterclockwise? It's clockwise to you, but counterclockwise to me, okay? And so when you get into 3 dimensions, you can't think about things as just clockwise and counterclockwise. You have to think of them as clockwise or counterclockwise from, looking from a direction. And so we're going to think about it in terms of the right-hand rule. So what we've always, let me write that here. So to rotate a coordinate system, theta about, and then this is according to the right-hand rule. So if the z-axis is going this way, you know, we've always talked about a positive angle, a positive rotation as being counterclockwise. What it really is it follows the right-hand rule with your thumb in the positive z direction. So that's the way to think about a positive angle now, is your thumb in the positive or negative axis direction. Okay. It's the same thing as counterclockwise if the arrow is coming towards you. Okay, so to rotate coordinate system an angle theta, according to the right-hand rule, about first the x-axis. The rotation matrix is 1, 0, 0, 0, cosine theta, sine theta, 0, negative sine theta, cosine theta. To rotate about the y-axis according to the right-hand rule, the rotation matrix is cosine theta, 0, negative sine theta, 0, 1, 0, sine theta, 0, cosine, cosine theta. And then about the z-axis, rotation matrix is cosine theta, sine theta, 0, negative sine theta, cosine theta, 0, 0, 0, 1. And notice there's sort of a pattern here. Look at the x-axis and the z-axis. So with both of those, you have a 1 diagonal spot of the axis you're doing. Zeros across from that 1. And then cosine, sine, negative sine, cosine in the remaining 4 spots. Okay, that's how it is for the z-axis and the x-axis. And then the y-axis always just has to be a little different. Remember with that coming back with the British accent? Yeah, the Scott. Yeah, right. Just always has to be a little, thinks it's a little too good to just follow the pattern. So that's why the y-axis, you got the negative first and the positive later. Okay, so let's go back to the example from Friday. What was that? Yeah, so the original coordinate system was this, x, y. The z-axis then has to be coming towards us. And the rotated coordinate system still had the z-axis coming towards us, but the x-axis was up and the y-axis was this way. Last time we did it all in terms of thinking of the axes, the coordinate axes of A expressed in the B coordinate system. Now let's think about what angle this is rotated about what axis. So what kind of rotation do you need to take this coordinate system? Yeah, 90 degrees counterclockwise or 90 degrees in the positive z direction. Okay. So theta is positive 90 degrees about z. And so the rotation matrix is cosine of 90, that's 0. Sine of 90 is 1, 0. Then negative sine of 90 is negative 1. Cosine of 90 is 0, 0, 0, 0, 1. And that should be the rotation matrix we came up with last time. Just thinking about it a different way. Now, you can also use rotation matrices to re-express tensors. Vectors and tensors are both sort of defined by how they relate to rotation matrices. So, okay, you can also re-express tensors in a new coordinate system using rotation matrices. And to do that, the stress tensor in the new coordinate system is equal to the rotation matrix Q times the stress tensor in the old coordinate system times Q transpose. So notice, to re-express a tensor in a new coordinate system, it requires multiplying by 2 rotation matrices. It's the same rotation matrix, but one is, one's the matrix and one's its transpose. And in a sense, what that does is think of one of those rotation matrices as reorienting the stress cube. Remember that stress cube has like a positive x face, a negative x face, a positive y, negative y. So one of these rotation matrices realigns the faces. And one re-expresses the traction vectors on each face. Okay, so the stress cube, the stress tensor, is defined by which direction each of the faces of the cube is facing, and also what the traction vector is on each of those faces. And you have one rotation to do each of those jobs. All right, so let me do an example with the stress tensor. So let's say we have a stress tensor that's equal to 5, 0, negative 1, 0, 10, 0, and then negative 1, 0, positive 2. Let's say this is megapascals. And the coordinate system for this one is that. What we want to do is re-express this stress tensor in coordinate system from our last example, where x is this way, y is this way, and z is still towards us. And show that it's the same state of stress. So what I'm going to do is I'm going to start by drawing the stress cube in the original coordinate system. Then I'm going to re-express the stress tensor in the new coordinate system using a rotation matrix. And then I'm going to draw the new stress cube. And even though the faces are lined up in different directions, we're going to get the same cube. You know, if it said before that we have 5 megapascals going this way, now that direction is represented by a new axis, but we're still going to see that it's going that way. Okay, so first let's draw this stress cube. And the coordinate system is like this: x, y, z. So in the x direction, we have 5. On the x face in the y direction, we don't have anything. On the x face in the z direction, we have -1. So this is 1 in the negative z direction. And that means that this also has to be 1. And actually, since I'm sort of doing a double negative here, I already drew that arrow in the negative direction, so I'm going to get rid of this negative sign. And then in the y direction, on the y face, we have a +10. And in the z direction, on the z face, we have a +2. So that's it. Okay, so that's the state of stress for that point. And so now we're going to apply the rotation matrix. This is the same coordinate system transformation that we did in the example. So our Q is going to be whatever it just was. 0, 1, 0. Yeah. 0, 1, 0. -1, 0, 0, 0, 0, 1. Same as in the previous example. +90. So the stress tensor in the new coordinate system is 0, 1, 0, -1, 0, 0, 0, 0, 1. Times our original matrix in the old coordinate system, 5, 0, -1, 0, 10, 0, -1, 0, 2, times Q transpose. And so for this one, The first row is going to be the first column of this. So 0, -1, 0. The second row is going to be the second column, 1, 0, 0. And the third row of this is going to be the third column of this, 0, 0, 1. And your calculator does this instantly, but you can imagine why people wouldn't have wanted to do calculations like this by hand. But if you do this calculation, let me write this here. So this is Q. This is the old stress tensor. This is Q transpose. And yes. Oh, the Q and the Q transpose? No. You have to do it in that order. Right. Yeah, if you do Q transpose times this times Q, it'll give you the wrong answer. If you change the order in any way, it'll give you the wrong answer. Not for the rotation matrix. So you use the Voigt forms when you're using compliance and stiffness matrices, and you use the tensor when you're doing coordinate system transformations. And if you, has anyone done this? You're gonna add 10, 0, 0, 0, 5, 1. And then what? 0, 1, 2. Okay. Yeah. But other people got that too? Well, so now we're going to check it. So now we're going to draw this new stress cube. And now the coordinate system for this stress cube has the y-axis, no, the x-axis up, the y-axis that way, and the z-axis still towards us. Okay. In this case, I mean, because it was a 90-degree rotation, all those faces line up. You can't think about transformations this way if you have anything other than 90-degree rotations. You know what I mean? If you rotated something 20 degrees, none of these are going to match up. But if you rotated 90 degrees, you still have a cube where faces are lined up. It's just those faces now have different names. Okay, so on the X face, we have 10 in the positive X direction and nothing else. On the positive Y face, this is where it takes a little thinking. But now yeah, right. And so now, and the positive Y face is the one that's obscured. So on the obscured face, we have 5 going in the positive Y direction. But remember that for equilibrium, on the equal and opposite faces, we have to have equal and opposite tractions. So if this says we have 5 on this obscured face over here going this way, it means 5 going that way on the face we can see. And then we have 1 in the positive Z direction on the obscured face. So coming like towards us. That means on this face it's going back. And that means we have to have 1 going this way. And finally, in the Z direction, we have that. And if you compare this to the stress tensor we had in the old coordinate system, even though everything's named differently, it looks just the same. So we know in this case it worked. Yeah. Okay, so let's do an example. Let's say that we start out with this state of stress. Where this is 10 megapascals. This is 20 megapascals. And then 2's going this way. And then on the top, we have 50 megapascals going in. And then symmetry says that this also has to be 10. So what's the stress tensor in a coordinate system rotated positive 30 degrees about the z-axis? All right, so in this coordinate system, original one, the stress tensor is, so on the x face we have 0, 0, negative 2. On the y face we have 0, negative 50, positive 10. On the z face we have negative 2, 10, negative 20. Any questions about that? And so now we're going to use a rotation matrix, positive 30 degrees about the z-axis. So that's cosine of 30, sine of 30, 0, negative sine of 30, cosine of 30, 0, 0, 0, 1. Which is 0.866, 0.5, 0, negative 0.5, 0.866, 0, 0, 0, 1. And so Q transpose is 0.866, negative 0.5, 0, 0.5, 0.866, 0, 0, 0, 1. And so the rotated stress tensor, sigma nu, is equal to 0.866, 0.5, 0, negative 0.5, 0.866, 0, 0, 0, 1 times the stress tensor of 0, 0, negative 2, 0, negative 50, 10, negative 2, 10, 20. And then that's multiplied by Q transpose, 0.866, negative 0.5, 0, 0.5, 866, 0, 0, 0, 1. And has anyone multiplied that out? Or could you? Yeah. Negative 12.5. Okay. Negative 21.65. Negative, wait. Oh, these are symmetry, yeah. Okay, so this is 3.268, 9.66, and then what was the last one? Negative 20. Yes. Nope, that's right. Okay, so notice on this one, I'm not going to try to draw the stress cube in that orientation because it's really hard to, but what you should notice here is that when we rotated the coordinate system in, multiples of 90-degree angles, so when the coordinate system is rotated by 90 degrees, all the values, let's say all the magnitudes of the stress elements stay the same. They just move to new locations in the stress tensor. They just mean different things. Yeah, so like in the example right before this, we had a stress that was 10, one that was 5, one that was 2. And then when we did the rotation, we still had a 10 and a 5 and a 2 and a 1. They just were different things. Now one was in the z direction instead of the x direction. But when we rotated at an angle other than 90 degrees, let's say a general angle, all the values change. And this is important because how likely something is to break depends on things like what's the normal stress, what's the shear stress, okay? So this is important because the maximum normal stress and especially the maximum shear stress are used to predict failure. So what we want to do is the stress tensor in our coordinate system, whatever we've happened to choose as our coordinate system, isn't really the most important thing for figuring out when something is going to break. What we really want is we want to know what the stress tensor is at the one coordinate system that exists that gives us the biggest values for the normal stresses and the shear stresses. Okay? Like if you tried every possible angle, so we find the stress tensor in some coordinate system that we chose. And now if you think of trying all the other possible coordinate systems, as you rotate it around, sometimes the shear stresses are going to get smaller, sometimes they'll get bigger. Normal stresses will get smaller and bigger. What we want to find is the coordinate system. In this case, say it's this one. There's one out there that gives us the maximum values of the normal stress, and there's one out there that gives us the maximum values of the shear stress, and that's what's important to us. Yeah, but you have to know how to tell the computer to do it. No, that's right. And so that's the next topic we're going to get into. It's called principal stresses. Yes, there is. There are sort of intriguing relationships between them. The most positive normal stress and the most negative normal stress are 90 degrees apart. And the maximum normal stress and the maximum shear stress are 45 degrees apart. Yep. So when we're doing this, we're not actually moving material. We're just recalculating these stresses in a new coordinate system. Okay. The materials, so when we first calculate the stresses, it's like a snapshot of what's going on at that point in that material. We calculate that stress. And then we're done with the material. Not just mathematically, we're going to rotate that. We're going to find the coordinate system that gives us maximum values of normal stress and shear stress. And if those maximum normal stress and maximum shear stress are big enough, then we know the material is going to break. That's right. And when you said, I think what you're talking about when you say, right, just different perspectives, but what we saw with that example was when you take a different perspective, it changes what the values are. Yes, that's right. And so when you talk about a computer program, like you could imagine breaking it up into 1 degree increments and just doing the rotation matrix, applying the rotation matrix, and then at the end just seeing what was your maximum value of normal stress, what was your maximum value of shear stress. You could do it that way, but there's a more direct way to do it. Mm-hmm. Uh-huh. Yeah, well, it is a little confusing. Right. Right. That's right. Yeah. So let's think about. Okay, I'm going to try to draw. So I'm going to try to draw this on the one we just did. Mm-hmm. Because you're going from the forces don't change, but you're talking about what that stress tensor is giving you is tractions on specific faces, and you're changing where those faces are pointing. Yeah, right. And so, like for example, if Let me try to draw this rotated stress cube on the last one. So we started out with this as a state of stress, right? And then we recalculated the stress tensor rotated around the z-axis. So our new cube looks like, oh, I know how I'm going to do it. So let's just look at the values straight on to the front of the cube, looking straight at the z face. Okay, so before the coordinate system transformation, we had, so we're not going to see that 2 or the 10, but we do see, is that going to work? Okay, so we have the 20, on the z face, we have the 20, the 2, and the 10. Okay, so the 20 is going, was it in? And the 2 is going this way, and the 10 is going this way. And then what did we have on the positive x face? Okay, for symmetry, yep. Any normal stress on the x face? Okay. And and then what on the y face? And that's all? Like this? And that's all? And then there's stuff over here, stuff over here. So now our new stress cube looks like this. It's rotated 30 degrees about the z-axis. Yes, that's right. Let me draw this better. Okay, so this 50 is going down in, and then the 10 is coming out towards us. And now that it's rotated, we have on the positive x face 12.5 negative 21.65 and positive 3.268. On the y face, we have negative 21.65 negative 37.5 and 9.66. And on the z face, we have 3.268
So the stresses on the stay the same. They just cause different reactions or stresses on the stress cube due to how deeply it's rotated?
That's right. I mean, just like if you, let me finish getting these down and then I'll give a vector equivalent. 3.268, 9.66, and negative 20. And then, you know, stuff going on here and here. Let's say it's equivalent to what happens with vector components. So like if you have a vector like this with a magnitude of 10, let's say that angle is 30 degrees. In the coordinate system like this, that gives you 8.6650. Right. In a coordinate system like this, where this is 30 degrees, now that vector with a length of 10 is just straight in the positive x direction. So the vector components are 10, 0, 0. Even though the vector didn't change, the fraction of that vector pointing in these different component directions did change. And so I think that's a good way to think of what's happening here. And so just like what I did here was find the coordinate system where we had the largest single component of this vector, right? You can't find a coordinate system where you get a component of this vector bigger than 10, right? And that's the idea of what we're going to look for with stress tensors. We're going to look for the coordinate system where you can't find any bigger values of the normal stress. Okay, that's it. All of this will, but none of the principal stresses will. So you just need to know how to use those rotation matrices. And it's going to be, so for today, I'm going to assign the rest of the stress and constitutive relationship problems.